Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 8 from the universe to the atom. We're going to be going through inquiry question 4, properties of the nucleus, and we're going to be analysing this particular dot point, the spontaneous decay of unstable nuclei, properties of alpha, beta, and gamma radiation. For your textbook reference, have a look at these pages here. As we said before, we're going to explain the reasons for particular nucleus to become unstable and undergo radioactive decay, and we're going to analyze the different types of radioactive decay that can occur. Alright, so first things first, obviously let's look at the model of the nucleus. When we first started this series of in the Module 8, we first talked about J.J. Thomson with his structure of the atom, and he didn't have a concept of the nucleus. That changed when his student Ernest Rutherford came up with the idea that the nucleus is a densely packed positive charge, and then his student James Chadwick realized that inside the nucleus there are other kind of particles known as neutrons, which are neutrally charged that are stuck with the protons. What we do know though is, according to our understanding of electrostatic forces, is if the nucleus was made only of protons, there's going to be a really strong electrostatic repulsion. So imagine you had two protons here. If helium just had two protons, the nucleus would be very unstable because it's pushing against each other. The reason why the protons don't push against each other is due to the existence of the neutrons. So say for hydrogen, obviously this isn't the correct example, but say for if you had a nucleus or neutron inside the nucleus, that actually holds it stable together, and we're going to look into why that's the case. In this case, we actually have is hydrogen 2, the isotope, and so hydrogen 2 is actually a very stable isotope. So the reason being is because neutrons exert this strong nuclear force. What that essentially means, let's just give you a bit of an idea. If we draw out the scales of the different forces, the size of the strong force is, let's say, 1. Okay, and then we kind of base everything relative to the strong force. The electromagnetic force, which is responsible for the electrostatic force, that's about 100 times smaller than the strong force there. What we actually do know is the strong force is incredibly strong when it gets really close, when the particles are really close together. So let's say if I try to draw it out, okay, so in this range here, this range that we see here is the images that we see where the protons and neutrons are sort of just almost side by side. If they get too close, so if too close, it then becomes a repulsive force. If it's too far, it's too weak. And so the strong nuclear force only really occurs when the particles are really close together. Otherwise, the electrostatic force is a lot stronger. So that kind of explains to you what the neutrons are for. Okay, so get my laser pointer back. So this is just some handy info. The reason why the nucleus is so stable is because of this strong nuclear force of attraction between the protons and the neutrons. And that's strong enough to oppose the electrostatic repulsion between the protons. Okay, now at extremely short distances, the strong nuclear force is going to be repulsive. Okay, so we'll get into what kind of scenario could it be too repulsive. Just right, if it's just in a close enough distance, it will be attractive, and then as it weakens, it will get into larger distances, and that's what we know. It is the strongest force of the universe, hence we call it the strong force. If it was just up to gravitational force, that would be too weak to prevent the repulsion of the positive protons from pushing each other away. If we actually compare the combinations, let's have a look at the different combinations of carbon, okay? So here we have carbon-12, the most common type of isotope. We have carbon-13, and then we have carbon-14. Okay, now for those who have forgotten what an isotope is, an isotope is sort of an atom with the same number of protons. So you can see how each of these have the same number of protons, but they have a different atomic mass. That being, in this case, a different number of neutrons. So these are the ones that we know of, carbon-12, 13, 14. You can see carbon-12, carbon-13 are both stable, so the nucleus is quite stable here. You can see for carbon-14, though, the nucleus is unstable. And so what that can tell us is the ratio between the protons and the neutrons, what we call neutrons capital N and protons Z, will dictate how stable the nucleus is. We also call this the N-Z ratio, so mass to charge ratio. That's another way we call it, which basically is comparing the mass to the amount of protons that we're looking into. So that's what we're observing here. If we look at the sort of a chart that kind of explains to us, what's happening here, we can compare in terms of the number of neutrons to the number of protons. Okay, so the zone of stability you see in this curved line here, the zone of stability here is where we would believe the nucleus is stable. Anything outside this range is unstable. So if we have a scenario where the ratio is too high, so where N-Z is too high, meaning by we have too many neutrons, then we'll see the cause of a thing called a beta decay. We'll get into what beta decay is. If we get into a scenario where the mass is too high, now generally speaking it's about 80, if the atomic number is about 80 plus, then it will be an alpha decay, followed by maybe a beta decay. You never know. If the ratio is too small, we get a thing called a positron decay. Now you know that a positron is basically a positive antiparticle of an electron. So this is what we have here. This kind of explains to us what's happening. Just to kind of explain why it becomes unstable when you have too high a ratio. Remember, if we have too many neutrons, that means that the distance between the neutrons is too small, and so that causes that repulsion. So that's where the instability comes from. If you want to, work out how to write radioisotope equations or just work out the number of neutrons, there's a really clear way you need to go about it. So firstly, just to go over a really clear definition, protons and neutrons, when we talk about them as a collective, we can call them nucleons. The plural will be the nuclei. So to calculate the number of neutrons in the nucleus, we need to find the mass number and subtract that by the atomic number Z. Okay, when we're writing what we call the radioisotope equation, you need to write the symbol, you need to write the atomic number, and you need to write the mass number. Now this might be confusing for some people. Let me just explain why. If you look at your periodic table, and this is where the periodic table is used in the formula sheet, if you look at the periodic table, usually speaking, you have the symbol, okay, and then you have this number on top. That's the atomic number. So this is if you were reading your periodic table. And then down here you have your atomic mass, weight number. In this case, we don't really need to worry about the atomic mass, the weight number being equal, because we are talking about isotopes. This number is going to be different when we're doing isotopes, so can be different for specific isotopes. Okay, Now this 6 is the thing that will dictate the type of element you're looking at. So this is the number of protons you're dealing with. If I have a different number, then it's no longer carbon that I'm looking into. But if this number changes, that doesn't necessarily mean I'm dealing with a different isotope. So keep that in mind. Okay, so this whole process of where we have radioactive decay, we actually note this as transmutation of the nucleus. So transmutation occurs when one element changes into another through nuclear fission or nuclear fusion. We're going to talk about what these two are in the next few lessons. And in these nuclear reactions, we often get alpha, beta, or positron being released or absorbed. And don't forget the number of protons will dictate the type of element. So if you look at this animation here, it's as if you have one element that breaks into two different types and you even have the neutrons there. It could also be similar to what ancient alchemy thought, where you had a piece of lead and you could convert it into gold. That's an example of a transmutation. So that's actually a nuclear reaction. I want to give a shout out to one of my colleagues, Mr. Everett. He also came up with an analogy with his junior class where it was imagining if you had a watermelon and it went through alpha or beta decay, releasing these particles, it would change to a completely different type of fruit. So obviously the analogy isn't 100% what you would describe as accurate, but that kind of gives you an analogy of what we're talking about in transmutation. Okay, so let's go through, now that we've talked about how things spontaneously decay because of an unstable nucleus, let's talk about what the properties of alpha, beta, and gamma are, and also what are they, okay? You can sort of see, here and there some images, but let's go specific, okay? So let's just start off with before and after any nuclear reaction, there's always the same number of nucleons, so you're expecting the same number of protons and neutrons. So same number of nucleons. So what we can say is the atomic mass is the same. Okay, and the net charge stays the same. So the atomic number stays the same. Okay, we'll go through sort of examples of what that actually means. Okay, next what we can see here, we have an alpha particle. An alpha particle is written like so or written like so. Basically what an alpha particle is the nucleus of a helium, so you have 2 protons and 2 neutrons. Maybe I'll write that down as well. So what you're expecting is 2 protons, 2 neutrons. That's kind of the idea there. If we're talking about a beta particle, there can be 2 types. You can have the electron. As you can see, the atomic number is -1 because it's negatively charged. So negatively charged. Here we have the positron, and that's positively charged, so that's where the +1 is. You can also write it as beta, hence why we call it a beta particle. And then we have gamma. As you can see, there's no charge and there is no mass. So what that would tell you from that kind of symbol is gamma rays are called electromagnetic radiation, hence also why alpha, beta are called particles, but gamma is called a ray. So keep that in mind. Okay, so first we're going to go through alpha decay. So the general reaction looks like so. You have the nucleus break itself apart into a small constituent. Now, firstly, what I want to talk about is the fact when you write these equations, the mass number and the charge number stay the same, or the atomic number. So see how this is 238. So once it breaks apart, this is 234, and we get 4 here. But if we add them up together, the total is still equal to 238. So that's what we mean by the conservation there. You can see the atomic number, and these two atomic numbers, they add up to 92 at the end. So that's still being consistent with this value here. Okay, so these numbers stay the same. Okay, so same on both sides is the main message. Okay, keep that. All right. So generally speaking, when it comes to an alpha decay, the alpha particle, you can consider it a helium nucleus without the valence electron. So there's two electrons that's non-existent. And so it gives it a +2 charge. So it's got +2. So it's different sort of, it's more massive than a proton, and it has a greater charge than a proton. It's got +2 charge. Now, generally speaking, because the helium-2+ is, got this charge, it's highly ionizing, so it will latch on to some electrons to fill itself to react with. And generally speaking, we don't usually write it as 2+, we write it more like so. But the important part is, just so you remember, this 2+ represents that it's highly ionizing. So highly ionizing and it can cause more nuclear reactions. So cause more nuclear reactions in a way because of this +2 charge, or it's more ionizing, meaning by it can displace electrons from neutral particles, displace electrons faster in other materials. So it's sort of their way of being highly reactive, but not being sort of chemically reactive in that sense. Alright, the next one we have is an electron. And so you can see with an electron, it just comes out like so. Obviously, because it's a it's a negative charge 1. So if something goes through a beta decay, you would expect that the atomic number would go up by 1. So you can see this is still 90 overall. We do say the electron has a mass number of 0 because it's very small. So compared to a proton and neutron, so we're not going to bother putting that in. Now, generally speaking, the reason why we have a beta decay is when the charge number is obviously the charge to mass number is too high. So to get that additional charge, what actually happens is a neutron will decay into a proton and an electron, and subsequently that electron is kind of pushed out into the surroundings. This does produce a thing called an antineutrino. Okay, so this antineutrino here. Just to give you an idea, a neutrino is actually an elementary particle, which we will talk a bit more about in the final inquiry question. So this is in inquiry question 5, a bit more detail into that. But just keep that in mind, it always accompanies a beta decay. If we have a positron decay, that's because a proton has converted itself in, or formed a neutron, and then it's formed a positron being released out. And also what we have here is a neutrino. So that's a neutrino there. Okay, so that's your neutrino. Now, keep this in mind though, a neutron is not made up of a proton or an electron, so it's not these two added together. It's actually made up of quarks, so made from quarks and antiquarks, made so keep that in mind, but in the actual decay process, it will break itself to a proton and electron, but it's not made from those two things. Alright, the next one, or the final one we'll talk about, is a gamma decay, okay, or gamma ray being released. And now these generally accompany most alpha decays, and some beta decays depending, but the question should tell you either way. Gamma is just energy, or what you would remember from Module 7, it's a photon. It's electromagnetic radiation. So if you have a highly energized nucleus, and the mass to charge ratio is relatively stable, if the nucleus is still too highly energized, it will eject some energy, and that's in the form of gamma radiation there. Okay, so let's go through some examples of writing equations. So we have the alpha decay equations. Write the mass number and the atomic number of the following. So if we have a look at what we have here, obviously I don't have a periodic table with me, so I'll just quickly go over how we figure this out, and then we'll go through what the answers are. So we've released a helium atom, so that's a mass number of 4. So the new mass number we have for this new isotope is 218, and then the atomic number is 2 being released, so subtract that by 86, and so the element we have should have atomic number of 82. Same idea here. If we go backwards, we can find that these two added up together should be 86, and then these two added together would be 214. So if we actually have a look, that's already given to you here. So we have polonium 218. So PO 218 polonium, I think that's how you spell it. And then I'm not quite sure what the name for this one was, but we do know the symbol here. So let's just quickly check. Oh, before I go on, you can see that gamma rays, because it has 0 charge and 0 mass, we sometimes don't really write the numbers for it, but if you really want to, you can as well. So there we have it. Okay, pretty self-explanatory there. You can see that the numbers are different, but the main point that keeps them as the same isotope is the fact that these two numbers are the same. So hence that's the same isotope we're looking, or that's an isotope of itself, so to speak. Okay, the next one is we have Anticium 227, and then we have plutonium 244. So let's have a look at the writing of the equation. I might just quickly check as well the atomic numbers. Actually, I'll just go through the answers. So what we have here is Anticium 227. It's 89. And then we have, is it the francium that I wrote there, or was it thorium? Let me quickly check. Alright, so it is indeed francium. I will just quickly change this little error here. So we have francium 223, alpha, and then the gamma ray. Here we have plutonium 224. Is it 222? No. Little errors here and there. Do excuse. So we have plutonium 244, and then we have uranium 220. It should be therefore 240 there. Okay, and then we have alpha and then gamma as well. All right. Okay, the next one we have is trying to write the beta decay of lithium 8, xenon 135, phosphorus, and chlorine. So I'll just do the first one. So lithium 8, atomic number of 3. It decays and forms beta. So it forms a beta particle. We'll just write the electron, -1. What that means is the atomic number is going to increase because we subtracted by a negative number. So still same atomic number. It's gone into an atomic number of 4, so that should be beryllium. But don't forget, when we have beta decay, we will form a neutrino as well, so, or antineutrino. So that's an antineutrino, which was one of the elementary elements, particles, and so that's what we have there. Okay, so there you go. Alright, so the last bit we're going to go through is looking at different properties of alpha, beta, and gamma. That's what we need to look into. So if we have a look in terms of the penetration power, we can see that the alpha particle can be blocked by a piece of paper, beta goes through the piece of paper blocked by aluminium, and then gamma needs to be blocked by lead. Now lead is really dense metal. So what we can kind of gauge is in terms of penetrating power in going through different materials, alpha is the lowest penetration. Only a few centimeters in air will block it. Gamma has the highest penetration. It can go through air really easily. It needs a thick layer of lead to block it out. In the actual medical industry, depending on the type of tumor a patient has, the type of radiation treatment that they use can also differ. So say, for example, if the tumor was near the surface of the person's skin, they will potentially use alpha or beta because it has low penetration going inside your body, but it does react really well to things near it. If the actual tumor was inside the body, then potentially they might use gamma because it's highly penetrating through the skin, and then it goes deep into particular body tissues that it wants to target. So that kind of gives you an idea of how different medical industries will use radiation slightly differently. And the reason why penetration power does differ is because of this concept of ionization. Now, ionizing ability of these radioactive types is based on its ability to remove electrons from neutral molecules. So alpha has the highest ionizing power. Don't forget, because alpha has the +2 charge. So alpha has the +2 charge, which means it has a greater ability to extract electrons from neutral particles. Beta has a -1 charge, so it has a slightly different ability, so it has a lower charge, so it's less likely to kind of drag these electrons out. And then obviously gamma has a charge of 0, so it doesn't really do much ionizing there. And so that's why it can actually go through objects a lot better, because it's not interacting with many objects around itself. If we look at the way alpha, beta, and gamma work in electric fields, you can see that obviously alpha, being the positive charge, is going to bend towards the negative side of the electric field. Beta, being the negative charge, will bend towards the positive end. We also know, in terms of the actual bend, beta is greater, so it has a bigger bend because it's smaller mass than the alpha particle, while as gamma is just going to go straight through because it's neutrally charged. Okay, so there you go. Another one is looking at in terms of magnetic fields. So you can see from this diagram here, again, the beta bends more than the alpha because beta is smaller. So beta has a mass smaller than the alpha particle. Okay, hence why it also bends a lot more. So if you kind of recall, when we equate the equations of magnetic force and centripetal force, it kind of gives you an idea of that there. You can work it out from there. Okay, also obviously because of the charge difference. So alpha and beta is obviously going to bend the opposite direction. You can use the right hand palm rule to work it out. So obviously with the alpha particle, it is positive, so using your right hand, your thumb is pointing up, the magnetic field is pointing into the page, your palm is pointing to the left hand side, so that kind of explains what's going on there. So alpha, positive, fingers going in to the page, and then palm is going that. So the force on the alpha is going that way, whilst beta obviously going the opposite direction. Right, last thing you need to kind of do is just fill in this little table to summarize the different properties of alpha, beta, gamma. So what type of charge does it have? What's the penetrating power, ionizing power, and what path does it go through within this particular electric field? The other thing is obviously identifying the type of particle it is. This diagram we have here as it goes through this magnetic field. I'm going to go through the answer in 5 seconds so you have time to pause. Okay, so let's look through the answers. So just to quickly summarize, alpha has a charge of 2 plus, beta has a charge of 1 minus, and gamma is 0 because it's electromagnetic radiation. In terms of penetrating power, alpha has the lowest, gamma is the highest. If we're talking about ionization power, then it's reversed. So a low penetration power equals a high ionizing power. In terms of going through an electric field, it's always going to go to the negative side, beta is going to go to the positive, and then gamma is going to go straight through. If we look at this diagram here using the right hand palm rule, then we work out that particle X is an alpha particle, Y is gamma rays because there's no deflection, and then Z, according to the right hand palm rule, we have a beta particle there. Okay, so that kind of summarizes the reasons why a nucleus will become unstable depending on the ratio between the neutrons and the protons. And we also looked into the fact that when these do decay, it will release alpha particles, beta particles, get positrons and gamma rays there. So that kind of gives you the details in that. And then obviously don't forget the different types of properties that these radiating types will have. If there's anything you didn't quite grasp during the first watch of the video, I do encourage you to just replay certain bits of this video if you do need. If not, please join me in the next lesson when we start talking about nuclear half-life and nuclear fission reactions and chain reactions. But until then, stay safe and hope you enjoyed the video.